So thank you, Chang Yu, for the introduction and also for the invite here to speak to you all today. My name's, as introduced, Michael Barnes. I'm from Calvary Martin, Newcastle and the University of Newcastle in Australia. And my talk today is going to concentrate in, as Chang Yu said, on Varian's Machine Performance Check application, also known as MPC. Luckily for me, Chang Yu's done a great job of introducing MPC to you all, so that means I don't have to do it, so I can get straight into it. And as such, my talk today is going to be in two sections. I'm going to firstly take a look at how MPC tests currently comply with TG-142 recommendations. And then secondly, I'm going to take a look and present some ideas on potentially how MPC in its current form could be improved, taking some ideas out of literature. So getting straight into it, the question is MPC versus TG-142, where do we currently stand? So this is our standard TG-142 daily QA table, which I'm sure you're all very familiar with. I think it makes perfect sense to start with daily QA here because MPC is designed as a daily check device. And the question is, what does MPC test from this list? So what I can tell you is it certainly checks outputs for both electrons and photons in a constancy style. And these four publications all sort of indicate that with a little bit of care taken, that MPC does a fairly good job of this, at least for photon beams anyway. Now, this is going to be a bit of a feature through my talk today, where I've got these publications listed as with title and authors, but at the end of my talk there'll be a reference list for anyone who wants to look a bit more deeper into these publications. I can also say that MPC does the collimator size check. It checks both jaw position and, as Cheng Yu said, it checks MLC position. And again, these three publications sort of indicate that, certainly for a daily check level, it does this quite well. So what doesn't MPC check from this list? Well, basically it's everything else. Has no lasers checks, obviously, has no optical checks, so field, ODI or field light, and has no safety checks. Although I'd probably argue that it's a bit unfair to expect these tests to be performed by a daily check device anyway, so from here on in I'm not going to concentrate on any of these sort of type tests. TG-142 also has specifications for wedges and MLC. In terms of wedges, it calls for a daily functional test, which MPC currently does not do. However, being a simple functional test, I'm sure it could be easily added in the future. In terms of MLC, TG-142 is calling for a weekly qualitative test, and I think it's fair to argue that with its daily quantitative test, MPC is certainly exceeding this requirement. And again, these three publications indicate it does a fairly good job of it. In terms of imaging, I've argued in this publication that MPC meets the requirements for imaging and treatment coordinate coincidence. I think it's probably a better comparison to compare MPC now to TG-179. And I've argued in this paper also that it does a fairly good job of meeting the requirements of this task group report as well. So to summarise all that very quickly, I think it's fair to say that MPC does a fairly good job at meeting daily TG-142 requirements. But I'd also suggest that in this day and age, bearing in mind that TG-142 is now 10 odd years old or more, I would suggest that these requirements don't really set a very high bar for MPC to meet. So it might be a more interesting question to compare MPC to a standard daily check device that's commonly used in the clinic. So one such example is the Sun Nuclear Daily QA3, which is fairly commonly used. And QA3 has all these sort of tests in it, which already exceed TG-142 requirements. So then the obvious question is, what does MPC test from this list? Well, we've already spoken about it testing outputs, it does this well. But in terms of symmetry, flatness and energy, I've given it orange ticks here. And the reason that is because, in theory, the MPC uniformity test should be sensitive to these changes in these parameters. However, they're all sort of confounded in the one test, And also the literature is a little bit sparse to demonstrate that it actually does this well. So as I said, I've only given it an orange tick, meaning that theoretically it should cover this, but there's probably a bit more work to be done, and also this is an area which could potentially be improved. However, MPC certainly does a good job of checking the field size and field shift via its jaw position tests and its beam center tests. So what you can see here is it sort of ticks all the boxes, but in certainly those middle three, if you like, it possibly could do it better. So another interesting question could be that, considering that MPC meets our daily requirements quite well, does it go even further and meet some of maybe the monthly requirements? So this is our table out of TG-142. Again, we've already talked about it doing outputs well. And again, I've added orange here for the beam profile constancy and electron beam profile constancy checks, because although in theory the beam center and beam uniformity tests should assure these parameters, they don't do so directly, and so there's still a little bit of doubt as to whether you can be certain of these parameters using MPC. In terms of collimator angles and gantry angles at cardinal angles, I think MPC does a great job for the collimator angles. I also think it does a great job for the gantry angles. But however, again, the gantry angles are a little bit indirect. So it has this gantry zero test, which is done with like a gantry absolute test, which tests gantry zero quite well. And then it applies this gantry relative test, which in my opinion, and from the literature, indicates that it does a good job of checking out our gantry angles, but it doesn't present results in cardinal angles. So that's why I've left this as orange. We've also established that it does a good job of checking jaws. So therefore, what I would say is it's not difficult for MPC to meet current TG-142 data requirements. I'd also say it already meets some of the monthly requirements as well, so it's already exceeding the data requirements in this regard. And it's also providing similar type tests to our current daily check devices such as QA3. So what I would put to you is it's mainly a question of whether MPC can perform some of these tests better and potentially meet even more of the TG-142 requirements. Now the current philosophy in MPC, which underpins it, is that they want it to be as quick as possible, to be least onerous on the clinic as much as possible. So this means they've got a minimal number of fields that they can get away with. And what this does is it succeeds in making the process fast to perform, as Cheng-Yu indicated in one of his slides, but it means that some of these tests are influenced by multiple confounding Linac parameters. And the problem with this is it makes fails a little bit difficult to diagnose. And personally, I'd prefer MPC to take a little bit longer to perform, but give me sort of tests that I can much more easily diagnose and which I'm much more comfortable with in comparison with my other standard QA devices. So that segues nicely into the second part of my talk, which is how MPC can be improved. And I'm going to concentrate in here on the uniformity check, although I do believe there's other areas that could be improved. In the interest of time, I'm only going to concentrate on the uniformity test. So how the MPC uniformity test works is it basically takes a static field, 18 by 18 jaw-defined field for each beam energy that you have, and it images this with your EPID. This image is not corrected by the flood field, so it's a raw image, and what it does is it ratios this image with the baseline image. Then what happens is high frequency noise is removed by smoothing, and then the uniformity is presented as the variation between the two pixels with the highest and lowest magnitudes, but only within 75% of the field width, so to avoid the effect of any jaw. Now, as I see it, I have two problems with this. Firstly, it only presents one result, so the result is not differentiated by plane. And I think as physicists these days, and particularly with the way TG-142 is written, we're used to getting symmetry in terms of in-plane and cross-plane, but MPC doesn't do this. Also, as I've mentioned, the uniformity check is theoretically influenced by multiple Linac parameters which confound each other, which theoretically include changes in beam steering, i.e. flatness and symmetry, changes in beam energy because your flatness is sensitive to energy, and also changes in your EPID panel's performance via changes in its pixel responses. Now what I'd suggest is that what we actually want is individual tests for each of these three parameters, not one test which confounds them all. And I would also suggest that this can be done using PSM-corrected EPID imaging. So what is this PSM? PSM is short for pixel sensitivity map. And essentially what it is a two-dimensional array of pixel sensitivities on your EPID panel. And if you can calibrate this out, as these two publications indicate that you can, and I'd also hasten to add that there's also a poster at this very conference where they've introduced another method as well, so this is very topical at the moment, but if you can do this with one of these methods, then what you could do is, from your raw EPID image, you can remove the EPID detector non-uniformities, i.e. those non-uniformities in your image that have been introduced by your detector, but while still preserving the incident beam non-uniformities, i.e. the influence of your beam horns. And why this is important is that if we include or maintain our beam horn influence in our images, then suddenly we can start applying our sort of flatness and symmetry or our beam profile metrics and get some information about our beam. So what I'd propose is that in MPC, we perform a PSM calibration by whichever method proves best, and then perform some analytics on this PSM corrected image. And in the literature, some people have taken a look at this, and the two publications here provide some methodologies which I believe could be used in MPC in place of the uniformity check. And I'm now going to sort of quickly discuss both of these publications. So the first one comes from the good people at Washington University primarily. And what they did is they PSM corrected their EPID image and took a profile through it. And you can sort of see here this green one, which is their profile. It's not a flat profile, which was what you would get if this was flood field corrected, but it sort of has the influence of the horns in it. So you can provide just do some analytics on it. And what they did is they measured the flatness on this beam, on this profile, and then they adjusted their bend magnet to change the energy of their beam until they saw a 1% change in PDD10, which is obviously your TG-142 metric and tolerance for beam energy. And then they measured flatness again. And what this did is it allowed them to see a change in flatness with a change in energy, so they could calibrate this method to the TG-142 metric. And what you can sort of see here is that this methodology, if you've PSM corrected your image, could easily be included into MPC. In this publication, what we did is we looked at the symmetry aspect of PSM corrected images in terms of beam steering. And what we did is for our 4 available photon energies, including FFF, in both planes, so as I said, differentiated by plane, which is something that uniformity doesn't currently give us. What we did is we measured the symmetry on these beams. And I'd hasten to add here that these are absolute symmetries. These are not relative symmetries or compared to baseline, which you previously had to do with flood field corrected EPID images. Then what we did is we put our IC profiler on and we measured symmetry using a more standard method and compared the two. And what we found is pretty good agreement. Our worst case was 0.4% with a mean of about 0.2%, and we thought this was pretty good. We also demonstrated the sensitivity of the method by adjusting our beam steering until we saw a 1.1% change in symmetry on our profiler, and our PSM corrected EPID method showed agreement within 0.2% of that as well. So we demonstrated sensitivity of the method. Now what you can see is with these two methods here, suddenly if we've PSM corrected our images, we've suddenly got a way of doing an energy check and also checking symmetry in both planes. So what we've done is we've isolated out 2 of our variables in our uniformity check. So the third variable there is our EPID panel pixel-to-pixel stability. Now this parameter is largely removed in the MPC as it currently stands because they smooth it. However, I'd argue that smoothing is not ideal here because it has potential to remove some of your incident signal, so I think it's much better to characterise it and remove it rather than smooth it. And what I'd propose is that if we have our PSM measured at install and then we repeat the measurement either 6 monthly after that or annually or some frequency like that, then we then compare our PSMs from initial, then we can get a good measure of whether our EPID panel has changed in sensitivity. And suddenly that's our third variable taken out of that uniformity check. In terms of the frequency, this publication here indicates that the PSM should be stable over a sort of a year basis, so probably 6 monthly or annually is reasonable. So then if we implement these proposals that I've just put to you and suddenly compare back against our QA3, suddenly you see we've got all blue ticks, at least in my opinion. So we've got an absolute symmetry measurement in both planes, which probably is even a little bit better than the QA3. And we've also got flatness and energy via the WashU method. So then what I would propose to you is that what Varian could do is they could take an PSM correction method, measure it at install for each new LINAC, and then store the measured PSM in their MPC application. Then when we run MPC on a daily basis, the PSM can be removed from the image, I should say from the current image that's used for uniformity, and then we can apply our symmetry and flatness metrics to get symmetry and energy out of this test. And then what we do is we update our PSM semi-regularly, 6 monthly or annually, and compare our PSM back to our baseline. And if we did all this, what we would have is that we'd have all of the influences in the uniformity test isolated out. And we will have done this without adding any extra tests or any extra fields on a daily basis. And we will be providing tests which are similar, if not better, than our current QA3 device. Thank you.